Okay, guys, so today we're going to have a look at conservation of momentum. Okay, so we saw yesterday, we saw impulse and momentum. We got introduced to the idea of momentum and what momentum was. Momentum being a vector with both magnitude and direction, right? So if an object is moving in any particular direction, then it has momentum because of its mass, right? And so what we're going to see today is for an isolated system, much like the conservation of energy, we have this law of conservation of momentum, right, for an isolated system. So if two particles of masses m1 and m2 form an isolated system, then the total amount of momentum of the system is conserved regardless of the nature of the force between them. Whenever two particles collide, their momentum remains constant, provided they are isolated. Okay, so what we're going to see is like, why don't we start with, we'll derive what where the conservation of momentum comes from. But why don't we have a look at, like, we'll draw the diagrams first. Maybe that'll help us, right? Contextualize where this stuff's coming from on the right side. Okay, so before a collision, we might have a mass m1, right, traveling with some velocity vi, right? It could be even like, we'll call it v1, or we'll leave it vi, v initial. Okay, actually we'll put the 1 there, and we're going to put the 1 there to denote m1 and v1, right? So this, all the information is matching up to particle 1, say, right? And then we're going to have particle 2 also traveling with some speed. We'll call it v2, right, to match up with particle 2, m2, and that's still going to be the speed initially. Okay, and then these two particles are going to collide, right? And what we're going to see is after the collision, they're going to bounce off of one another. And let's just assume that it stays completely in the x direction. And we'll say that now particle 1, right, or m1, is now moving in the opposite direction, right? And we'll call this m1 again, and we'll call this v1, but it's going to be final or prime, right? So we can mark it prime. Okay, and then we also know that m2 is going to be moving to the right with some velocity v2 prime afterwards, right? And this is going to be m2. Okay, so that's what's happened, right, before and after. Now, during the collision, we want to have a look at what exactly has happened during the collision. Well, in the split moment that these two objects or particles have collided, they are touching, right? And we know that there is anytime we have a contact between any two objects, we're going to have a force, right, in the form of a normal force, right? And that's going to be equal and opposite to the actual, like, the direction of the force. The normal force is going to be opposite to the actual contact, right? The force that one is applying to the other. The thing is here is they're both applying forces to one another, and what we're going to see here, we're going to have m1 and m2, but we're going to have a force in this direction, right? And it's going to be the force that particle 1 applies to particle 2, and vice versa on the other side, right? We're going to see that on the other side, this is going to be the force that 2 exerts on 1, okay? And what you're going to see is that these two forces are equal and opposite, right? That's from Newton's third law, right? For every action, there's an equal and opposite reaction, okay? And this, is good that we did it in this order, because this formulates this argument, right? Where we say, if two objects collide, they're obviously going to exert some amount of force on one another, right? And the force that they exert would be equal and opposite, right? Through the normal forces, okay? Or the contact forces, okay? And then if we were to take this one step further, we learned yesterday that, okay, well, if how long is this force being applied? We called that the impulse or jerk, right? We could see that, right? This would be like, we defined this as jerk yesterday. But we also found that jerk was the change in momentum, right? And so we would see that delta P1 had to equal delta P2, negative delta P2. That's because this. Okay? And so if we ran with this now, right, like we know what the change of momentum is, right? The change of momentum for the first particle would be, okay, well, there's M1, V1, right? Prime, so like the mass of particle 1, the velocity of particle 1 after, subtract off M1, V1, right? What its speed was initially, right? We could even denote it with a little I if that helps you, okay? And then on the other side, we're going to see that, well, it has to be the negative change in momentum, right? But it's going to be the same thing. We're going to have M2 this time, V2 prime, minus M2 V2 initial. Okay, these are just the two changes in momentum, right? That's the change in momentum. Final minus initial. And then on this side, we also have the momentum or change in momentum for particle 2. That's going to be final minus initial over here as well. Okay, but it has to be negative because it's equal and opposite. Okay, in order for it to be conserved. Now, if we just ran with this, right? So this is kind of like the physics argument has now been set up. And from here now, we can do a little bit of math. And anytime I see brackets, I try to get rid of them. Oops, didn't mean to do that. How do I get rid of brackets? Well, I just expand. It's expanding a binomial. So let's put the negative inside, and we'll rewrite this line. M1 V1 prime minus M1 V1 initial has to equal negative M2 V2 prime minus, plus, sorry, because we're going to multiply this on there, plus M2 V2 initial. Okay, and our goal here is to get all the initial momentum on one side and get all the final momentums or all the prime terms onto the right side. Okay, and that's what we're going to do. We're just going to move stuff around here, and then we'll see what happens. Okay, so let's get the initial stuff on the left side and the final stuff on the right side. Okay, so it looks like by that we're just looking at the terms. Well, that's a final term, right? And I know it's a final term because of the prime. So let's move that to the other side, and we'll grab the initial term from over there and bring it over, right? And so what we're going to get is negative M1 V1 initial, right? That's that term right there. And I'm going to bring this over and subtract it off as well. Minus M2 V2 initial. That has to equal negative M2 V2 prime minus, right? I'm going to grab this term and bring it over. M1 V1 prime. Oops. Okay, so now we've got initials on one side, finals on the other, and we can, looks like I could factor out a negative from everything, okay? Okay, and I'm just going to reorder it after too. Okay, I'm going to flip these around. Just for, not that it matters too much, but just to keep it consistent, left side versus right side. Okay, so I'm going to factor out the negative, and I'm going to get negative M1 V M1 initial, right? Remember, this is the initial momentum of particle 1. And then I'm going to add, or sorry, well, now I'm going to add, right? Because I factored out the negatives out, right? And so I'm going to add M2V2 initial. Should put some eyes on here. Right? And that has to equal the same thing on the other side. I'm just going to reorder it, right? So M1V1 prime plus M2V2 prime. Okay, and now if I were to divide both sides by the negative, right, they'd end up canceling out, right? And what are you left with? You're left with M1V1 initial plus M2V2 initial is equal to M1V1 prime plus M2V2 prime. So momentum initial, so like before the collision, right? You're taking into consideration all the momentum in the system, and this is before the collision. And then we have all of the momentum after the collision, right? Okay, and this formulates, this right here is, let me just pick a different color. This is our conservation of momentum law. Okay, where momentum before has to equal momentum after. Okay, and that was just the derivation of where it came from relative to what we worked on yesterday. Okay, with a little connection back to Newton's laws there. Okay, so we're going to take this, and again, it just comes down to like extracting information and having a clear diagram. Okay, these questions weren't too bad. They get a little bit more difficult when collisions start happening in 2 dimensions. This is right now we're concentrating on 1 dimension. Okay, so things like traveling in the pure X and Y. We're going to see later that we can have things move off at angles, but that's really not that big of a deal. You guys have the tools to deal with that. Okay, but the most important thing is that the just like an energy argument, right? The energy before has to equal energy after. It's like this, the momentum before, for an isolated system, the momentum before has to equal momentum after. Okay, so when we look at a question like this one, okay, I'm just going to turn my page over here because I've got the solution right now. There's no calculator needed. We have a 0.045 kilogram golf ball, right? And the head of the driver has a mass of 0.15 kilograms and travels at a speed of 56 meters per second before the collision. Okay. The ball has a speed of 67 meters per second as it leaves the face. Okay. What is the speed of the head of the driver immediately after the collision? Okay, so let's set up what's going on here. We know that if I were to draw a little picture, it'd be sitting on a tee, right? I'll try and draw a nice. Okay, so the golf ball's sitting here. It's not going to move, right? It's just sitting there, right? So we know it has no momentum. Why does it have no momentum? Because it has no velocity, right? And so if I look at object 2, no velocity means 0. That term cancels out. Okay, so there's no momentum there. But then you've got the driver head coming in. Right? We'll put it on a stick. It's going to come in and collide with this thing, and then afterwards, the golf ball is going to be moving with some velocity. Right? V. We'll call it V. Well, let's call this M1 and M2 just for consistency's sake. And so the driver is also moving through with some velocity as well. It goes the other way. Okay, and so M1 here and M2 for the the golf ball, right? So we know that the golf ball now has a velocity, and this is drawing the picture keeps everything organized, right? So the golf ball's mass 2, it's going to have a velocity 2, right? M1 is going to have a V1 prime. We should put little primes on there afterwards, I suppose. right? And then over here, we're going to have a V1, right? But it's a V1I. And here, we're going to have M2 V2 initial. Okay, so we're kind of letting go of the fact that V2 means final and V1 means initial for these kinds of questions like what we saw with kinematics, and I think that's why sometimes it gets just a little tripped up. And the picture keeps everything nice and organized, and you're not going to mess that up, right? It's about keeping track of, okay, what's the mass 1 and its velocity initially, and what is it after the collision? So what's M1 V1 prime? And also M2, like you have two objects, you could have three objects colliding. We're just going to do two. M2 V2I and M2 V2 prime, right? It's about keeping track of the objects separately, okay? And so I think you got to break the connection in your head with the fact that V2 means final velocity, okay? Which is why I try to introduce the notation of final and initial in kinematics. So anyway, that's that. Okay, so now we can actually, like, the little slash means basically an equal sign, right? And we know now M1 V1I plus M2 V2I has to equal M1 V1 prime plus M2 V2 prime. Okay, this is your conservation of momentum law. And we saw that this term here, the golf ball is not moving. And so if you were to plug in the velocity of that golf ball initially, it'd be 0. And so this term cancels out, which means all the momentum being contributed to the system comes from the driver head, right? All right here. Okay. Now we could do this question and solve it algebraically, okay? Now, sometimes when you do that, this gets a little bit messy, and so it's understandable. Sometimes if you plug the numbers in and do that from the standpoint, the V2 prime thing gets a little bit funny, but we can try it anyway. What we're going to do here, we're looking for V1 prime. Okay, this is what I'm looking for here. I'm looking for what is the speed of the head of the driver immediately after the collision. Well, that's this term right here. That's what this is describing. V1 prime after the collision. So that's what I'm looking for. Okay. So if I were to rewrite this, I might choose just to bring that over right away, right? So I'm going to go M1 V1 initial, subtract off M2 V2 prime, right? Remember, if I move that over, it's got to become minus or negative. And then that has to equal M1 V1 prime. Now, I would not. These questions are a little bit different from the standpoint relative to the energy questions. Like, we can't cancel the masses here because these aren't the same masses. That's why I've denoted it. Okay? Doesn't quite work like that now. Okay, so to get this term by itself, we're just going to divide both sides by M1. And we arrive at the algebraic expression that describes what the velocity of the driver head is after the collision. Okay, and so I can say V1 prime is equal to M1 V1 prime, initial, sorry, minus M2 V2 prime, all divided by M1. Okay, and this is your equation that we can use. And so if I were to bring that up here and start making substitutions, well, the mass of the golf ball, and again, I'm referring back to my picture because the picture's like this picture keeps everything nice and organized. So I'm always referencing back to this from the standpoint of I need to now know where to plug in what information, right? It's very, very easy to put something in the wrong spot if you don't have something like this picture set up. You have a before and after, and it organizes everything for you, right? So if I'm looking to plug in M1. Well, what's M1? M1 is the driver head. Okay, well, the driver head has a mass of 0.15 kilograms. Okay, so let's plug that in, right? You can see how the picture here, helpful, right? So 0.15 kg, well, you don't need the units. We won't put the units in. They're helpful. I mean, you probably should, but we're just out of room here. And then V1 initial. Oh, that's the speed of the driver head, 56 meters per second. Pencil's being funny here. Okay, and then we're going to subtract off the mass and velocity of the golf ball after, right? M2 V2 prime. V2 prime is over here, the golf ball after the collision. Okay, so we just got to plug those numbers. What's the mass of the golf ball? 0.045. I'm going to move this over in a sec. And multiply that by multiply that by the velocity of which the golf ball leaves, right? And we have devices to measure this sort of stuff, right? Like golf simulators and things like that can measure the ball speed and spin rates and everything. They're quite incredible, actually, the machines. And so that this golf ball leaves at 67 meters per second, and we need to divide that all by the mass of the driver head, M1, right? Which is going to be 0.15. Right, and if you do that calculation, you should find that the velocity of the driver head after the collision, so V1 prime, would be equal to 35.9 meters per second, if we've done that correctly. Okay? Okay, but who's to say that these objects, right? Like, there are lots of instances where we have a collision, but the objects don't necessarily just bounce off one another, right? Like, I don't know, a car accident, sometimes the cars get intertwined, right? And so, who's to say that the objects bounce off one another? Could it not be possible that two colliding objects got stuck together, right? So, for example, a car accident, as I was just saying, right? Get entangled. Now, what do we do in that instance? Because that's a type of collision, right? Right? Collisions occurred, right? Something has to happen. So we have two kinds of collisions. We have elastic collisions, right? And we have inelastic collisions, right? And we just did an example where we saw an elastic collision, okay, where the momentum and the kinetic energy are conserved, right? And the objects bounce off one another. Okay, that's what we just saw with that golf ball question. Okay, and so we can write out our two laws that remain constant here, that hold true for these instances, right? So we can have our conservation of momentum is valid here. So M1 V1 plus M2, and we can put the little i's. M2 V2 initial has to equal M1 V1 prime plus M2 V2 prime. Sometimes these take a little bit of thinking to write down, right? The conservation of momentum. So this is our momentum. It's conserved under elastic collisions, but we also said that kinetic energy is also conserved, right? So we can have, okay, well, 1/2 M1 V1 squared, right? And that'll be the initial, plus 1/2 M2 V2 squared, right? And that'll also be initial, has to equal 1/2 M1 V1 prime squared. This is what I was talking about yesterday, right? With these primes and squared sticking in there. Not the best system, but, and then we can also add the 1/2 M2 V2 prime squared. Okay, just try to make those a little bit bigger, those squared, so we can see. You can also put a little f in there too if you want final instead of the primes. You could put f's if you'd like. It's a little bit more helpful too. Okay, so we get the conservation of kinetic energy, and we also get the conservation of momentum for elastic collisions. Okay, now an inelastic collision is one where only the momentum's conserved, and it's when the two objects collide and stick together. Okay, and so under these circumstances, we can set up the initial scenario very similar, right? From the standpoint of like both objects are going to have some momentum, right? So we know that M1 V1 initial plus M2 V2 initial. Okay, that's before the collisions occurred, right? But then afterwards, something interesting happens. Well, the two masses combine, right? And so we can add the two masses, M1 plus M2. Okay. But now these two things are combined and connected with one another and moving together in one direction, right? So we don't need two velocities. We can just call it capital V or V, just one velocity after. I don't know if you even want to call that like V3 or something, right? The velocity of the combined masses. Okay. That's what would happen in an inelastic collision after the two objects have collided. Okay, and they've stuck together. You have to add the two masses together because they've stuck together, and now they are moving off at some new velocity v3, right? And remember, velocity is a vector, so you're going to have to include directions of things like this, okay? I know we didn't really do that above, but the question was in one dimension, okay? Okay, so let's have a look at the second question here, right? We can draw what happens. And we're again, like the picture's like, picture says 1,000 words, right? And it'll help you set up the question. Okay, so during a football game, a fullback of mass 108 kilograms running at a speed of 91 meters per second is tackled head on by a defensive back of mass 91 kilograms running at a speed of 63 meters per second. What is the speed of this pane just after collision? I don't know what the word pane is doing there. Pair. Should be pair, not pane. There we go. What is the speed of this pair just after the collision? Okay, so let's set up our statement, right? And let's even draw our picture first, right? So we've got like M1 moving, right, at a velocity of 9.1 meters per second. So we'll call it V1, right? Initial. And then we're going to have this other football player of M2 moving towards the other guy. V2 initial, right? And then so that's great. It's fine, Danny. After the collision, the two move, they combine to be M1 and M2. And we want to find out what's their velocity after the collision. Okay. And so we're going to see, okay, well, what's V? V3, we'll call it. That's what I want to know. Okay. Now, in these questions here, I'm just noticing they're using terminology of like speed. Okay. And so they're not really giving us much information in the standpoint of directions. Okay. I think these questions are a little loose from the standpoint of just getting you introduced to momentum. And then when we go to do the 2D questions, you will see that these velocities will have directions on them, okay? So that you can be very specific in finding, when we find V3, we know where the two masses go. If it's over here or this way, we can be very specific in depicting exactly what has gone on, right? Right now, just speeds, you can see how like the scalar quantities kind of have their limitations, right? So here's what we got. We just want to find the final speed, not necessarily the velocity, okay? Let's keep using those interchangeably, and they're not. Okay, so let's just run through this now. We're going to set up our statement where M1 V1 V1 initial plus M2 V2 initial has to equal, well now afterwards, after the collision, the equal sign is the slash, is M1 plus M2 multiplied by V3. Okay, and so for me to get V3 by itself, the thing that I'm ultimately interested in, the speed after the collision, I would have to divide both sides by M1 plus M2. Okay, and I get V3 equals. Now I'm probably overdoing it with the number of times that I write this out, but I find that you guys can see that the amount of information and keeping track of the information is critical to these questions. Okay, and so once I'm looking at this, we'll say, okay, here's M1. We can just start labeling things M1, V1. Okay, so let's plug that stuff in. So V3 is going to equal, M1 is 108 times the initial velocity of that 108 kilogram football player, which is 9.1. And then we're going to add the mass and speed of the football player, the second football player, right? So 91 times 63. We're going to divide that by the two masses, so 108 plus 91. Okay, and if you were to run through that calculation, you should find that the final velocity of the pair would be 7.82 meters per second. Did I say velocity and speed? Okay, the final speed. Okay, well, this is an introductory, right, where we're like looking at things in one dimension. So one dimensional isn't necessarily that interesting, like the direction in terms of like we're either going to be going north, south, east, or west, right? Once we get involved with the two-dimension stuff, the direction starts becoming more important, and that's we're probably going to see that very soon. Very soon. I don't know exactly when, but very soon. Okay, so that's your introduction into conservation of momentum. You can see for elastic collisions, if I give you guys an elastic collision, you can pivot between these two equations to help you solve. Okay. Moving forward, okay, it doesn't have to be, you can use these two conservation laws interchangeably for elastic collisions. You cannot do it for inelastic, okay, because kinetic energy is not conserved for inelastic collisions, okay. So that's it. That should be up there in Minds Online, and I've put a supplementary video there too, just for you guys to watch. In case you need help with any other concepts, okay? And I'll put the homework questions up there, okay? Let me know if you have any questions.